In this video, we will revisit the amplitude of probability to go from position qi to qf over time t using the many-path formulation of quantum mechanics. This is a preliminary for what we will do later when we will generalize the many-path approach to quantum field theory. We do that in non-relativistic quantum mechanics, but now we have a potential for the particle. The action of the potential on the state qi is straightforward because q is an eigenstate of the operator q. However, it is not for the operator p, so we would like to separate this exponential in two terms with an exponential depending only on p times another exponential depending only on q. The problem is that p and q do not commute, so these two quantities are not equal. So the trick is to consider only an evolution over a short time delta t and to use a Taylor expansion of the evolution operator. So if delta t is small enough, I can neglect the second order in delta t. I can also rewrite this expansion differently. Of course, these two quantities are not the same, but they only differ up to a second order in delta t, which I neglect anyway. I now recognize each of these terms as a first order Taylor expansion of an exponential. Of course, the equality only holds when I write explicitly the second order in delta t. But if I take delta t small enough, I can neglect this second order, and therefore I can approximate the initial exponential with a product of two exponential, one only depending on p and one only depending on q. Of course, my initial time t is not necessarily small, but if I write it as a sum of small interval delta t, with delta t small enough, then I may be able to use the separable form of the exponential. The idea is then to write the evolution operator as a product of evolution operator over small times delta t, and insert the completeness relation between each exponential. Let me also relabel qi by q0 and qf by qn. So I end up with a product of many transition amplitudes over small evolution delta t. Each of them has a form, and because delta t is arbitrarily small, I can replace this exponential by the product of the two exponential I obtained before. Acting v of q on qi give me a number I can take out of the bracket expression. As usual, I now insert my completeness relation in momentum space. And remember that the overlap of q and p is equal to exponential ipq. We recognize a Gaussian integral . The prefactor is not relevant for us now, so we will only take the exponential term. I can rewrite the second exponent using q dot time derivative of q at I equal to qi plus 1 minus qi on delta t. This is only true, of course, for small delta t. We recognize the expression for the Lagrangian. Let's go back to our amplitude. So each of the exponential over small delta t in our amplitude will give us an exponential of the Lagrangian at the given point q1, q2, etc. But the Lagrangian is only a number, so we now have a product of exponential of numbers, which I can simply write as an exponential of a sum. This is up to a constant c because I didn't take into account the constants in the Gaussian integral. We take the continuous limit by taking delta t goes to 0, which also means that n goes to infinity. we end up with an infinite number of integrals, which together with a constant I write as a path integral, and the discrete sum in the continuous limit becomes an integral. We recognize the action as the time integral of the Lagrangian. Let's draw a space-time diagram to visualize what we have been doing. We are looking at an evolution from Qi to Qf over a time t. First, what we did was to discretize the time into n intervals. Then we inserted the completeness relation between each interval. Imagine that for simplicity we discretize space with only 5 points. We start in Qi, but because of the first completeness relation we can end up in any point in space after the first evolution over delta t. Then the second completeness relation takes any of these points into any point in space. For the last interval there is no completeness relation, therefore every final evolution will end up in the same final event in t. We see that we have many possible paths to go from the initial event to the final event. And when we take the continuous limit where we have delta t goes to 0, this interval becomes infinitely small. Therefore the path becomes continuous and we have an infinite number of paths joining these two events. Note that by construction the paths can go up and down in space but can't go backward in time. So to summarize, we look at all the possible paths joining our two events. We calculate the action for each of these paths, and for each of these paths we associate exponential of I times the action, which we sum for all the possible paths. That's the meaning of our path integral here.